Now, in this lecture, we'll answer on two questions. In the first question, we will find out the length of line segment X in triangle ABC, and in the second question, we will find out the shaded area in the quarter circle. Okay, so we start with the first question. So in the drawing we have triangle ABC. We know that angle DAE equals to 60 degrees. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. Side EC equals to 4 units, and side BD equals to 5 units. And our mission is to find out the length of line segment DE that is equal to X according to what is given as the question. So first of all, in triangle ABC, those two angles are equal to each other, so I write it down. This angle ACB, equals to this angle ABC, and both those two angles are equal to 30 degrees. Okay, here I repeat again. In triangle ABC, we know that angle ACB equals to angle ABC, and both angles are equal to 30 degrees. And according to the rule that in front of equal angles in the triangle there are equal sides, we conclude from it that here in front of this angle we have side AB, in front of this angle we have side AC. So AB equals to AC according to the rule that in front of equal angles in the triangle there are equal sides. We conclude that AB equals to AC. Okay. AB equals to AC. We also note that the sum of the angles in any triangle is equal to 180 degrees. We will define angle BAD as alpha. We will define angle EAC as beta, and because of the fact that the sum of the angles in triangle ABC is equal to 180 degrees, we will write down that the sum of the angles here it is equal to 180 degrees, so that is to say here 30 degrees plus this angle that is also equal to 30 degrees plus angle BAC, this angle equals to alpha plus 60 degrees plus beta, and in total the sum of those two angles equals to 180 degrees. So here we have this equation: 30 degrees plus 30 degrees plus alpha plus 60 degrees plus beta equals to 180 degrees. 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So here in this side of the equation we have 180 degrees plus alpha plus beta, 120 degrees plus alpha plus beta equals to 180 degrees. We subtract 120 degrees from this equation and we get that alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. So found out that alpha plus beta equals to 60 degrees. Here we will make a construction from point A. We will draw a straight line in such a way that angle CA, here, this angle so we draw the straight line from point A in such a way that angle CAL, this angle will be equal to alpha. This is the first construction. In the second construction is that from point C we draw a straight line in such a way that angle ACL will be equal to 30 degrees. Anyway, we will make this angle 30 degrees and then we will extend this straight line until it intersects on the first straight line that we drew, and in this way we actually created triangle ACL. Okay, so we made two construction here. We draw a straight line from point A in such a way that angle CAL will be equal to alpha degrees. Then from point C we draw a straight line in such a way that this angle will be equal to 30 degrees. Then we extended the straight line C until it intersects with the first straight line that we drew. Okay, so we have already found out that alpha plus beta equals to 60 degrees. So we can write down here that this angle alpha plus beta equals to 60 degrees. In the next step, we will focus on triangle ABD. And triangle ABD and triangle ALC. I repeat again, we will focus on those two triangles and we prove that those two triangles can go into each other. So why those two triangles can go into each other? First of all, AB equals to AC. We already proved that AB equals to AC. So we can write down that AB equals to AC. In addition, those two angles, they are equal to each other, they are both equal to alpha, therefore they are equal to each other. This angle equals to alpha according to our construction. So angle BAD, this angle equals to this angle, that is actually angle CAL, and both angles are equal to alpha, therefore they are equal to each other. I'll repeat again, we already found out that AB equals to AC. In addition, angle BAD equals to angle CAL, and they're both equal to alpha, therefore they're equal to each other. And finally, this angle, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So angle ABD, this angle, equals to this angle, it is actually angle ACL. Both angles are equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACL, and they're both equal to 30 degrees, therefore they're equal to each other. So we actually proved that those two triangles can go into each other according to angle side angle rule. Here we have those two angles are equal to each other, they're both equal to alpha. Those two sides are equal to each other, and those two angles are equal to each other. They're both equal to 30 degrees, therefore they're equal to each other. So triangle ABD, this triangle, congruent. This is the sign of congruent to triangle ALC. This triangle, and they congruent to each other according to angle side angle rule. Repeat again. We have those two angles and the side that attached to these two angles in triangle ALC that congruent to those two angles, and the side that attached to those two angles, that is AB, in triangle ABD. Therefore, those two triangles can go to each other according to angle side angle rule. And from the fact that those two triangles can go into each other, first of all, we conclude that side BD equals to side LC. Side BD equals to side LC. Those two sides will be equal to each other according to the rule that in front, according to the rule that incongruent corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides, that is to say BD and LC, will be equal to each other. So BD equals to LC. But according to what is given as the question, BD equals to 5 units. So we can write here that BD equals to 5 units according to what is given us in the question. And from this equation 5 equals to BD equals to LC, we will conclude that LC also equals to 5 units. Okay, here LC also equals to 5 units. In addition, from the fact that those two triangles can go into each other, we conclude that AD equals to AL. AD equals to AL. Side AD equals to side AL according to the sum rule that corresponding sides in congruent triangles are equal to each other. And if we define AD as A, here AD equals to A according to our definition. From this equation A equals to AD equals to AL, we will derive that AL also equals to A. AL also equals to A. Here AL equals to A. Okay. The next step, we'll join points E and L together by a straight line. And we will prove that the green triangle ADE, is congruent to the orange triangle AEL. And prove that the green triangle is congruent to the orange triangle. So I write it down. We'll prove that the green triangle ADE, this green triangle, congruent to the orange triangle AEL. So why those two triangles congruent to each other? First of all, side AD equals to side AL equals to A. AD equals to AL equals to A. So both sides are equal to A, therefore they are equal to each other. Those two sides are equal to each other. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. So angle ADE, this angle, equals to this angle, that is actually angle EAL. So both angles are equal to 60 degrees, therefore they are equal to each other. Both two angles are equal to 60 degrees, therefore they are equal to each other. And finally, we have side AE, that is a common side, therefore this side equals to itself. AE equals to AE. It's a common side that belongs to both triangles. So we actually proved that triangle ADE congruent to triangle AEL L according to angle side angle rule. Here we have those two sides, side AD and side AE, and the angle between those two sides, this angle in the green triangle that converge to those two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. It's actually side angle side rule. We have two sides and the angle between them in the green triangle that can go to two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we'll conclude that side DE equals to side EL. DE equals to EL. DE equals to EL according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say DE and EL, will be equal to each other. But according to what is given us in the question, DE equals to X, that is the side that we are looking for. So DE equals to X, and from this equation, X equals to DE equals to EL, we will derive that EL is also equals to X. EL, side EL is also equals to X. In the next step, I will present to you the law of sines, the law of cosines, and we will implement the law of cosines in triangle LEC. So what is the law of cosines? The law of cosines is true in any triangle so I can write down here that in any triangle so if we have triangle ABC, that could be any triangle. This is triangle ABC. The length of side AB equals to A units, side AC equals to B units in its length. The angle between side AB and side AC is theta, and side BC equals to C units in its length. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So I repeat again. In triangle ABC, that could be any triangle. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines in triangle ELC. So I'll copy triangle ELC here and we'll implement the law of cosines in triangle ELC. So this is triangle ELC. Angle ECL, this angle equals to 30 degrees plus 30 degrees, that is to say it is equals to 60 degrees. Side EC equals to 4 units according to what is given in the question. Side LC equals to 5 units according to what we already found out. And side LE equals to X, that is the line segment that we are looking for. So in the right triangle, triangle LEC, according to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, so this equation is the implementation of the law of cosines in triangle LEC. Okay, so here we have x squared that is equal to 4 squared is 16 plus 5 squared is 25 minus 2 times 8 is 2 times 4 is minus 8 and minus 8 times 4 is minus 40 times cosine 60 degrees is cosine 60 degrees equals to 1/2. So in conclusion, we found out that x squared equals to 64 plus 25 is 41 minus 40 over 2 is minus 20. So x squared equals to 41 minus 20, that is to say x squared equals to 41 minus 20 is 21. So here we take a root out of this equation and we'll get that x equals to either square root of 21 or in terms of numbers is equal to 4.58 units. Okay, so the answer to the first question is that the length of side DE that is equal to x, it is equal to either square root of 21. Of course, we are relating to the positive root of 21 because of the fact that this number is a length and the length must be a positive number, or in terms of numbers it is equal to 4.58 units. Okay, so we finished with the first question. The next step I will present to you the second question. here in the drawing we have a quarter circle. Inside this quarter circle we have a circle with radius of 2 units, and we also have, so here we have a circle with radius of 2 units, and also we have a semicircle that with radius of 2 units, and our mission is to find out the shaded area. Okay, so because of the fact that this shape is a quarter circle, we know that this angle equals to 90 degrees. It is true in any quarter circle, and we define this point as point O. Point O is the center of the quarter circle. We will define the radius of the quarter circle as capital R. Capital R is the radius of the quarter circle, and we define this point as point L. Point L is the point of tendency of tangent OL in this circle. It is given as the question, so here we define the center of this circle as P. It is given as the question that PL is the radius of this circle. So here the radius PL, it is drawn to the point of tendency, that is to say it is drawn to point L. Point L is the point of tendency. Of tangent OL with this circle. And we have the radius PL that is equal to 2 units that is drawn to the point of tendency. And according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Whenever you have a radius that is drawn to the point of tendency, here it is drawn to point M, that is drawn to that is the point of tendency of tangent AB with this circle. Then, in this case, tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So here we implement rule number 1 in our drawing. So we have the radius PL that is drawn to the point of tendency. That is to say, it is drawn to point L, that is the point of tendency of tangent OL with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OL will be perpendicular to the radius LP. So if OL is perpendicular to LP according to rule number 1, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay? In the next step, from point P, that is the center of the circle, we will draw perpendicular on here. This we will define the center of this circle as M. So from point P we will draw perpendicular on OM. Okay? So here this is perpendicular, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and MO as point N. So actually in quadrilateral NONP we have 1, 2, 3 right angles. So inside quadrilateral NOLP we have 3 right angles. Okay, and the sum of 3 right angles is 90 times 3 is 270 degrees plus the size. So I write it down here in quadrilateral NOPL. We have 3 right angles and the sum of 3 right angles is 270 degrees plus the size of the fourth angle, that is actually angle NPL. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtract 270 degrees from this equation, and we get that the missing angle NPL equals to 360 degrees on 270 degrees, it is equal to 90 degrees. So this angle equals to 90 degrees, it is a right angle. So actually inside quadrilateral NOPL we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NOPL as a rectangle. Okay, quadrilateral NOPL is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So that is to say, in rectangle NOPL, its opposite sides are equal to each other. That is to say, PL equals to NO. PL equals to NO, according to the rule that the opposite sides of a rectangle are equal to each other, PL equals to NO. But PL equals to 2 units according to what is given us the question. So I can write here that PL equals to 2, and from this equation 2 equals to PL equals to NO, we will derive that NO is also equals to 2. NO equals to 2, so I can write here that NO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we conclude that NP equals to OL. NP equals to OL according to the rule that the opposite sides of a rectangle are equal to each other. So if we define NP as X, then we can write here that NP equals to X. So from this equation X equals to NP equals to OL, we will derive that OL is also equals to X. OL is also equals to X. Okay. Now we'll focus on the circle and on the touching point of this circle with the quarter circle. Actually, this circle and the quarter circle have an internal length between them. That is to say they are touching each other internally At this point we define the touching point of the two of the circle, and the quarter circle is point K. And whenever you have an internal launch between two circles or semicircles or quarter circles, then it means that the straight line that connects the two centers with each other must pass through the touching point. That is to say, the straight line OP must pass through point K. So here, according to this rule, we get that here the straight line OP, that is the straight line that connects the two centers together, must pass from point K, that is the touching point of the circle with this quarter circle. Here, the straight line OP that connects the two centers, point O is the center of the quarter circle, point P is the center of the circle, so this straight line OP, must pass through the touching point, that is point K. So OPK is one straight line, but OK is also the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point O, and ends at point K, that is the point of the quarter circle itself. That is exactly the definition of a radius. So OK is the radius of the quarter circle, that is equal to capital R according to our definition. Point P is the center of the circle. Point K is the point of the circle itself. So that is exactly the definition of a radius. So PK is the radius of the circle, that is equal to 2 units. Okay, PK equals to 2 units. And what is the length OK, OP? That is actually the distance between the centers of the quarter circle and the circle. From the drawing, it is very easy to see that OP, line segment OP, equals to OK minus PK. OK minus PK. I'll do it again. OP equals to OK minus PK. So OP, that is the distance between the centers of the quarter circle and the circle, is equals to OK. OK equals to capital R, it is the radius of the quarter circle, minus PK. PK equals to 2, it is the radius of the circle. So in conclusion, we found out that OP equals to R minus 2. Here OP equals to R minus 2. Okay. Now we will implement the Pythagoras theorem on the right triangle OPL, this right triangle. According to the Pythagoras theorem, in the right triangle OPL, by PT is a version for Pythagoras theorem. In the right triangle OPL, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, therefore the square of the hypotenuse is OP square, that is equal to the sum of the squares of the perpendiculars, that is to say it is equal to OL square plus LP square. I'll repeat again. According to the Pythagoras theorem, in the right triangle OPL, OP square equals to OL square plus LP square. This will be equation number 1. OP, the hypotenuse OP equals to R minus 2. So OP square is R minus 2 square. That is equal to OL square. OL equals to X, so OL square will be equal to X square plus PL square. PL equals to 2, so PL square is 2 squared, that is 4. So in conclusion, I found out that according to equation number 1, R minus 2 square equals to X square plus 4. We'll open the brackets in this side of the equation number 1 and we get that R minus 2 square equals to R square plus 2 squared, that is 4, minus 2R times 2 is minus 4R, that is equal to X square plus 4. Here we have 4 on both sides of the equation, so 4 will get cancelled. And finally we found out that X square equals to R square minus 4R. This is equation number 1. So, in the next step, we'll focus on the circle, on the quarter circle. Thus, the circle and the quarter circle have an external length between them at this point. This is the touching point of the circle and the quarter circle. We define the touching point as point H, and we have a rule that states that whenever we have an external length between two circles or semicircles or quarter circles or two circular shapes, then an external length, then the straight line that connects the two centers together, that is to say, in this case, the center of the quarter circle is point M and the center of the circle is point P, that is to say, the straight line NP must pass for the touching point, that is to say, it must pass for point H. So here, according to the rule that I mentioned, here, the straight line PM passes for point H. That is to say, here, P H M is one straight line. P H M is one straight line, according to the rule that I mentioned, that the straight line that connects the two centers together, that is to say M and P, must pass for the touching point, that is point H. For the touching point of the quarter circle of the circle, that is point H. So P H M is one straight line. Point P is the center of the circle. Point H is the point on the circle itself. This is exactly the definition of a radius. That is to say, PH is the radius of this circle, that is equal to 2 units. here point M is the center of the quarter circle. Point H is the point on the point M is the center of this semicircle. Point H is the point on the semicircle itself. That is to say, MH is the radius of the circle. It means that it's equal to 2 units. So in conclusion, we found out that the straight line NP equals to 2 plus 2, that is 4. Okay? So I will draw the right triangle NMP in a new page here. This angle equals to 90 degrees. Why this angle equals to 90 degrees? This angle equals to 90 degrees according to our construction. From point P we draw perpendicular on MM, or on MO. From point P we draw perpendicular on MO, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. So angle MNP equals to 90 degrees according to our construction. NP equals to X. The hypotenuse MP equals to 2 plus 2, that is 4. What is the length of line segment MN? Point M is the point of the semicircle. This point G is a point on the semicircle itself. That is to say, MG, this is exactly the definition of a radius. MG is the radius of the semicircle, that is equal to 2 units according to what is given as the question. Point O is the center of the quarter circle. Point G is a point on the quarter circle itself. This is exactly the definition of a radius. So OG is the radius of the quarter circle, that is equal to capital R. So we know that OG minus MG minus NO equals to MN. Okay, MN equals to OG minus GM minus NO. Again, OG equals to MG minus NO minus MN. OG is the radius of the quarter circle, that is equal to capital R according to our definition. Minus MG. MG equals to 2 units, that is the radius of the semicircle. Minus NO. NO equals to 2 units according to what we have already found out. So it is NO equals to 2. So in conclusion, we found out that MN equals to capital R minus 2 is minus 4. Capital R minus 4. MN equals to capital R minus 4. MN equals to capital R minus 4. Now we will implement the Pythagoras theorem on the right triangle, triangle MNP. By PT is a version for Pythagoras theorem. Okay. So in the right triangle, triangle NMP, this right triangle, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is mp squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to mn squared plus np squared. Repeat again. In the right triangle MNP by PT, MP square equals to MN square plus NP square. So here MP equals to 4, so MP square is 4 squared, that is 16, is equal to MN square. MN is R minus 4, so MN square is R minus 4 squared plus NP square. NP equals to X, so NP square is X squared. So in conclusion, we found out that according to equation number 2, 16 equals to R minus 4 squared plus X squared. Here we'll open the brackets inside of the equation and we get that according to equation number 2, 16 equals to R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus X squared. Here we have 16 on both sides of the equation, so 16 will get cancelled. In the next step we will add 8R to this equation, and we get that according to equation number 2, 8R equals to R squared plus X squared. Here we subtract R squared from this equation number 2, and we get that according to equation number 2, 8R minus R squared equals to X squared. This is equation number 2, but according to equation number 1, we have already found out that X squared equals to R squared minus 4R. Okay, so in the next step we'll create equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. So this will be equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. And we'll get that according to equation number 3, X squared according to equation number 1 is R squared minus 4R, while X squared according to equation number 2 is 8R minus R squared. So in conclusion, we got equation number 3 that states that R squared minus 4R equals to 8R minus R squared. Here we will add R squared to this equation number 3, and we get that according to equation number 3, R squared plus R squared is 2R squared, so 2R squared minus 4R equals to 8R. Here we will add 4R to this equation number 3, and we will get that according to equation number 3, 2 times R squared equals to 8R plus 4R is 12R. So we found out that 2r equals to 12, 2r squared equals to 12r. Here we will divide this equation number 3 by 2. And we get that according to equation number 3, r squared equals to 6r. Here we'll subtract 6r from this equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. Here we take r as a common factor. So what is left from r squared after we took from it r as a common factor? What is left? It is actually r. What is left from minus 6r after we took from it r as a common factor? What is left? It is actually minus 6 equals to 0. So in conclusion, we found out that r times r minus 6 equals to 0. So we have two solutions that are possible to this equation. Either r equals to 0, but r is the radius of the quarter circle. And the radius of the quarter circle must be a positive number. It can never be equal to 0. So we cancel this solution. And we have the second solution, that r minus 6 equals to 0. Here we add 6 to this equation, and we get that r equals to 6 units. So we found out that the radius of the quarter circle is equal to 6 units. The radius of this quarter circle equals to 6 units. And what is the shaded area? The shaded area equals to, it is very easy to see from the drawing that the shaded area equals to the area of this quarter circle minus the area of this circle minus the area of this semicircle. I repeat again that the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. And we have already found out that the radius of the quarter circle equals to 6. And the area of a quarter circle equals to pi r squared. That is the radius, that is the area of a circle over 4. Okay? Minus the area of the circle. The radius of the circle is 2, so, and the area of the circle is pi r squared, so it is pi times 2 squared, minus the area of the semicircle. The radius is also equals to 2, so the area of the semicircle equals to pi r squared over 2, so it is pi 2 squared over 2. Okay, so in conclusion, we found out that the shaded area equals to pi r squared over 4. R equals to 6, so pi 6 squared is 6 squared is 36, so it is 36 pi over 4. It is the area of the quarter circle minus 2 squared times pi is minus 4 pi minus pi 2 squared is 4, 2 over 2, 4 over 2 is 2, so it is, this expression in total equals to 2 pi. Okay? Here 36 over 4 is 9, so this expression in total equals to 9 pi minus 4 pi minus 2 pi. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the shaded area, if the shaded area equals to either, if the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Repeat again. The shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, I finished with the second question. In the next step, I will summarize the lecture. We start with the first question. So in the drawing we have triangle ABC. Inside triangle ABC we have triangle ADE. Side BD equals to 5 units. Side EC equals to 4 units. Angle DAE, this angle equals to 60 degrees. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. And our mission is to find out the length of this line segment DE that is equal to x according to what is given as the question. Okay, so first of all, in triangle ABC, we have those two angles are equal to each other. Here, angle ACB equals to angle ABC. Both those two angles are equal to 30 degrees. And we have the rule that in front of equal angles in the triangle, there are equal sides. That is to say, in front of those two equal angles, there are two equal sides. That is to say, in front of this angle we have side AB, in front of this angle we have side AC. That is to say, AB equals to AC according to the rule that I mentioned. So here we can mark those two sides that are equal to each other. AB equals to AC. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So in triangle ABC, the sum of the angles is equal to 180 degrees. We defined angle BAD as alpha. We defined angle EAC as beta. And we know that the sum of the angles in triangle ABC equals to 180 degrees. That is to say 30 degrees plus 30 degrees plus alpha plus 60 degrees plus beta. In total, it must be equal to 180 degrees. Okay? So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in conclusion, we found out that 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtracted 120 degrees from this equation and found out that alpha plus beta equals to 60 degrees, because 180 degrees minus 120 degrees is 60 degrees. So therefore we found out that alpha plus beta equals to 60 degrees. Then actually we did a construction from point A, we draw a straight line in such a way that angle CAL equals to alpha. Again, angle CAL equals to alpha according to our construction. Then from point C, we draw a straight line in such a way that angle ACL will be equal to 30 degrees. Then we extended the straight line until it touches the circle, until it touches this straight line at point L. So in this way we created triangle ALC. Again, we did two constructions. We created the straight line AL in such a way that angle CAL equals to alpha, and then from point C we do a straight line in such a way that angle ACL, this angle will be equal to 30 degrees, and then we extended those two straight lines until they intersect with each other at point L. Okay, so here we already found out that alpha plus beta equals to 60 degrees. So here this angle alpha plus beta is equal to 60 degrees. And in the next step, we proved the triangle ADE, triangle ACL is actually here we have. In the next step we proved the triangle ABD is congruent to triangle ALC. So why those two triangles can go into each other? First of all, angle ABD equals to angle LCA or ACL. They're both equal to 30 degrees, therefore they are equal to each other. Okay. In addition, side AB equals to side AC. We have already found out that side AB equals to side AC. And finally, we have angle BAD. This angle, those two angles, they are both equal to alpha, therefore they are equal to each other. So we actually proved that the two triangles, triangle ABD, congruent to triangle ALC according to side angle rule. Here we have those two angles and side AB and side AC that attached to those two angles in triangle ALC congruent to those two angles and side AB that attached to these two angles in triangle ABD. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude that side BD equals to side LC. Side BD equals to side LC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other. Therefore, the corresponding sides, that is to say BD and LC, will be equal to each other. So BD equals to LC, but according to what is given us the question, BD equals to 5 units. So we can write here that BD equals to 5, and from this equation 5 equals to BD equals to LC, we will derive that LC also equals to 5 units. Here LC also equals to 5 units. The second thing that we can conclude from the fact that those two triangles can go into each other is that side AD, this side AD equals to side AL. According to the sum rule, that corresponding sides in congruent triangles are equal to each other, we conclude that side AD equals to side AL. And if we define side AD is A, then from this equation A equals to AD equals to AL, we derive that AL also equals to A. Here AL also equals to A. In the next step we put that the green triangle can go into the orange triangle. So why those two triangles can go into each other? First of all, we just right now found out that side AD equals to side AL equals to A. Okay, AD equals to AL equals to A. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. Here, this angle is alpha plus beta, that is 60 degrees, and this angle also equals to 60 degrees, therefore those two angles are equal to each other. Here, angle AD equals to angle EAL, and angle EAL, they are both equal to 60 degrees, therefore they are equal to each other. And finally, we have side AE, that is a common side that belongs to both triangles, so this side equals to itself. AE equals to AE. So actually found out that the green triangle and the orange triangle can go into each other according to side angle side rule. We have those two sides and the angle between them in the green triangle can go into those two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that the two right triangles can go into each other, we will conclude that DE equals to EL. DE equals to EL. Those two sides are equal to each other according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say DE and EL, will be also equal to each other. Okay, so here DE equals to EL. But according to what is given as the equation, DE equals to X. And for this equation, X equals to DE equals to EL, we've derived that EL also equals to X. Here, EL is also equals to X. Okay? Then I presented to you the law of cosines, and we implemented the law of cosines in triangle ELC. This triangle, actually we added, we joined points A and L together, and in this way we created triangle ELC, and we implemented the Pythagoras theorem on this triangle ELC. Because of the fact that the law of cosines is true in any triangle, we can implement the law of cosines in triangle ELC. Okay, so what is the law of cosines? So the law of cosines, because it is true in any triangle, so here we have triangle ABC that could be any triangle. Side AB of triangle ABC equals to A units in its length. Side AC equals to B units in its length. Side BC equals to C units in its length. And the angle between side AB and side AC is theta. Then according to the law of cosines, C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. So we implemented the law of cosines in triangle ELC. L equals to X, LC equals to 5 units, and EC equals to 4 units. Here angle LCE or ECL, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. So according to the law of cosines, in triangle LEC, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. According to the law of cosines, of course. So here we got that x squared equals to 4 squared is 16, 5 squared is 25, minus 2 times 4 times 5. 4 times 5 is 20, and 20 times 2 is 40. So this expression in total equals to minus 40, and cosine 60 degrees is 1 half. So we substitute cosine 60 degrees by 1 half. So this expression in total equals to minus 40 times 1 half. So here we got that x squared equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21. So in conclusion, we found out that x squared equals to 21. We took a root out of this equation, and we found out that x equals to either square root of 21, the positive root, of course, of 21, because x is length. So x, it is either equals to the square root of 21 units, or in terms of numbers, it is equal to 4.58 units. I repeat again that dE that is equal to x, it is equal to either square root of 21 units, the positive root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question. Then I presented to you the second question. In the second question, we have this quarter circle. Inside the quarter circle, we have a circle and a semicircle. And our mission is to find out the shaded area. The circle is tangent to the semicircle at point N, and the circle is also tangent to the quarter circle at point K. Okay, so first of all, because of the fact that this is a quarter circle, it means that the center of the quarter circle is always at this point. So we define the center of the quarter circle as point O. And this angle must be equal to 90 degrees. It is true in any quarter circle. Okay. So here PL is the radius of this circle according to what is given as the question. So here we have the radius PL that is drawn to the point of tendency, that is to say it is drawn to point L, that is the point of tendency of tangent OL with this circle. And we have the rule that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here point M is the point of tendency of tangent AB with this circle, and we have the radius OM that is drawn to the point of tendency. That is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. We implemented rule number 1 in our drawing. We have here the radius PL that is drawn to the point of tendency. That is to say it is drawn to point M, that is the point of tendency of tangent OL with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OL will be perpendicular to the radius LP. So if OL is perpendicular to LP, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Okay? And so we have here two angles that are equal to 90 degrees, and from point P we draw perpendicular on MO. So here from point P we draw perpendicular to MO. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. Okay, so inside quadrilateral PNOL we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees. plus the size of the fourth angle, it is actually angle NPL. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and found out that the missing angle NPL equals to 360 degrees minus 270 degrees, it is equal to 90 degrees, it is a right angle. So here, this angle is right angle. So we actually found out that inside quadrilateral NPOL we have four right angles, and any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NOPL as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say PL equals to NO. PL equals to NO, but according to what is given as the equation, PL equals to 2 units. And from this equation, 2 equals to PL equals to NO, we derive that NO also equals to 2 units. Here, NO also equals to 2 units. NO also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that NP equals to OL. NP equals to OL, and if we define NP as X, if NP equals to X according to our definition, then from this equation X equals to NP equals to OL, we will derive that OL also equals to X. Here OL also equals to X. Okay? Here, this point K, is the touching point of the semicircle with the quarter circle. So we have here an internal notch between the circle and the quarter circle. And whenever you have an internal notch between two circles or semicircles or two circular shapes, then it means that the straight line that connects the two centers together, the straight line that connects their centers, in this case point O is the center of the quarter circle, point P is the center of the circle, and the straight line that connects the two centers together is PO. This straight line PO must pass for the touching point of the circle and the quarter circle. That is to say, the straight line OP must pass through point K. That is to say, OPK is one straight line. Okay? So we draw here line segment OP. Line segment OP must be one straight line. Line segment OPK must be one straight line because the straight line OP must pass through point K. So here we have the straight line OK. Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle that is equal to capital R according to our definition. OK is the radius of the quarter circle that is equal to capital R. Point P is the center of the circle. Point K is the point on the circle itself. This is exactly the definition of a radius. That is to say, PK is the radius of the circle that is equal to 2 units according to what is given as the question. So, what is the length of OP? The length of OP equals to OK minus PK. Again, OK minus PK equals to OP. Okay? Here, OP equals to OK minus PK. Okay, OP equals to OK minus PK. PK equals to 2. OK equals to R. So OK equals to R, PK equals to 2. So in conclusion, we found out that OP, the length of OP is capital R minus 2. Here OP equals to capital R minus 2. OP is also the hypotenuse of the right triangle OPL. We know that PL equals to 2 units. It is the radius of the circle, and OL equals to x. Okay, so we implemented the Pythagoras theorem on the right triangle, triangle OPL. We implemented the Pythagoras theorem on the right triangle, triangle OPL. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OP square equals to PL square plus LO square. And repeat again, in the right triangle, triangle OPL, OP square equals to OL square plus LP square. OP is the hypotenuse that is equal to R minus 2, so OP square is R minus 2 square. OL is x, so OL square is x square. LP equals to 2, so LP square is 2 squared, that is 4. So in conclusion, we found out that R minus 2 square equals to x square plus 4. We open the brackets in this side of equation number 1, and we found out that R minus 2 square equals to R square plus 4 minus 4R. That is equal to x square minus x square plus 4. We have 4 both sides of equation number 1, so 4 will get cancelled, and we left only with in this side of the equation we have x square, and the other side of the equation we have R square minus 4R. So in conclusion, we found out that according to equation number 1, x square equals to R square minus 4R. Okay. Then we focused on the semicircle and the circle itself. Here, those two shapes, those two circular shapes, have an internal and have an external arch between them at point H. Okay, that is to say, they are touching each other externally at point H. And whenever you have an external arch between two circular shapes, then it means that the straight line that connects their centers together, in this case it is PM, P is the center of the circle, M is the center of the quarter circle. This straight line PM must pass for the touching point of the semicircle with the circle, that is to say, it must pass for point H. That is to say, P H M or MHP is one straight line. MHP is one straight line. So here, edge and point P is the center of this circle. Point H is the point on the circle itself, that is to say, PH is the radius of this circle, that is equal to 2 units according to what is given as the question. Likewise, we have here point M is the center of the semicircle. This semicircle. Point H is the point on the semicircle itself. That is to say, MH is the radius of the semicircle, that is equal to 2 units according to what is given as the question. So in conclusion, we found out that MP equals to MH plus HP. Okay, but MH equals to 2, HP equals to 2, so that is to say, the hypotenuse MP in the right triangle MNP equals to MH plus HP. MH is 2 and HP is 2, so MP equals to 2 plus 2, that is 4. So the hypotenuse MN equals to 4 units. It is equal to 4 units, and NP equals to X, and here what is the value of MN? MN, line segment MN equals to OG, that is the radius of the quarter circle minus GM minus NO. Okay, if again NM equals to OG, that is the radius of the quarter circle, minus MG minus NO. We have already found out that MG equals to 2 units and NO also equals to 2 units. So OG is the radius of the quarter circle that is equal to capital R, minus MG that is 2, minus NO that is also 2. So in conclusion, we found out that line segment NM equals to R minus 2 minus 2, that is to say it is equals to R minus 2 minus 2 is minus 4. So MN equals to R minus 4. NM equals to R minus 4. So I draw here the right triangle MNP. We just right now found out that MN equals to R minus 4, NP equals to X, and the hypotenuse NP equals to 4 units. We implemented the Pythagoras theorem on this right triangle NMP. According to the Pythagoras theorem, MP square equals to MN square plus NP square. Again, in the right triangle NNP, according to the Pythagoras theorem, MP square equals to MN square plus MP square. The hypotenuse MP is 4, so 4 square is 16. NM equals to X, so MN equals to R minus 4. MN here, MN equals to R minus 4. Therefore, MN square equals to R minus 4 square. And NP, here NP equals to X. So NP square equals to X square. So in conclusion, we found out that according to equation number 2, 16 equals to R minus 4 square plus X square. We open the brackets on this side of equation number 2 and found out that 16 equals to R minus 4 square. R minus 4 square equals to R square plus 4 square, that is 16, minus 2 times R times 4, that is minus 8R plus X square. We have 16 on both sides of equation number 2, so 16 will get cancelled. Then we added 8R to this equation number 2, and we found out that 8R equals to R square plus X square. Here 8R minus 8R is 0. So in conclusion, we found out that 8R equals to R square plus X square. Here we subtracted R square from this equation number 2, and we found out that in conclusion that X square equals to 8R minus R square according to equation number 2, while according to equation number 1, we have only found out that X square equals to R square minus 4R. Then we created equation number 3 that states that X square according to equation number 1 must be equal to X square according to equation number 2. Okay? So here, X square according to equation number 1 is R square minus 4R, and it must be equal to X square according to equation number 2, that is actually 8R minus R square. Okay, so we added 8R to this equation number 3, and found out that here we added R square to this equation number 3, and we found out that R square plus R square is 2R square, so in this side of the equation we have 2R square minus 4R, that is equal to 8R. We added 4R to this equation number 3, and found out that 2R square, 4R minus 4R is 0, and it is equal to 8R plus 4R is 12R. So in conclusion, we found out that according to equation number 3, 2R square equals to 12R, We divided this equation number 3 by 2 and found out that 2r squared over 2 is r squared and 12r over 2 is 6r. We subtracted 6r from this equation number 3 and found out that r squared minus 6r equals to 0. We took r as a common factor, so what is left from this equation of 0, we took from it r as a common factor. What is left is actually r. And what is left from this expression after we took from it r as a common factor, what is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we have two solutions that are possible for this equation. Either r equals to 0 or r minus 6 equals to 0. But because of the fact that r is the radius of the quarter circle, it can never be equal to 0. So we cancel this solution and we have to leave the other solution that r minus 6 equals to 0. So if r minus 6 equals to 0, then it means that r equals to 6 units. So we found out that the radius of the quarter circle equals to 6 units. And what is the shaded area? This shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. We know that the radius of any quarter circle equals to the radius of the circle over 4. And the radius of any circle is pi r squared, and r is the radius of the circle. So the radius of the quarter circle will be equal to the radius of the circle, that is pi r squared over 4. Minus the radius of the circle. The radius of any circle is pi r squared, and r equals to 2, so it is pi 2 squared. And the radius of any semicircle is pi r squared over 2, and r is 2, so it is pi 2 squared over 2. Here r equals to 6, so r squared is 6 squared, that is 36. So this expression equals to 36 pi over 4 in total. And here pi r squared is pi times 4, that is to say it is 4 pi, so it is minus 4 pi. And there pi 2 squared is 4 pi, 4 pi over 2 is 2 pi. So in conclusion, we found out that the area of the circle equals to 36 pi over 4 minus 4 pi minus 2 pi. 36 over 4 is 9, so in total this expression equals to 9 pi. We have here 9 pi minus 4 pi minus 2 pi. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the area, the shaded area, this shaded area equals to either 3 pi square units, or in terms of numbers, 3 pi is 9.42 square units. I'll repeat again, the area, the shaded area, it is equal to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.